Okay, here we are on notes number 14. The topic is symmetry, even and odd functions, and domain practice. So let's take a look at example 1. We're going to plot point A, which has coordinates -6, 1. Okay, here it is. Next, we're going to plot the point that is symmetric to A with respect to the x-axis. So if you were to reflect the point across the x-axis, you would have point B. And its coordinates would be -6, -1. So notice that the 2 points have the same x-coordinate and the opposite y-coordinate. So if you reflect across the x-axis, or if you have symmetry across the x-axis, you have the opposite y-coordinate. Now let's plot point C. We're going to take point A and reflect it across the y-axis. So we get point C, and its coordinates are 6, 1. So notice that A and C have the same y-coordinate but opposite x-coordinates. So if you reflect across the y-axis, you get opposite x-coordinates. And then for point D, we're going to reflect across the origin, or we're going to look for the point that has symmetry across the origin. And when you have origin symmetry, it means if you turned it 180 degrees, it would look like it looks now, or you reflect it across both axes. And so if we reflect point A across both axes, we get this point down here, which is point D, and the coordinates are 6, -1. So if you compare the coordinates of the original point to the coordinates of point D, you see we have the opposite x and the opposite y when we have origin symmetry. Okay, now we're going to define even functions and odd functions. Some functions are not even or odd. Some functions are neither. So we have 3 categories: even, odd, and neither. Even functions have y-axis symmetry. So if we were to draw a simple example, it could just be your basic parabola. You could fold it on the y-axis and it lines up with itself. Now if I have a point over here, let's say this point has coordinates AB, then its image across the line of symmetry would have coordinates the opposite of A, B. Opposite x-coordinates, same y-coordinate. So when we put that in words, we say that for even functions, opposite x values have the same y value. And when we put that in symbols, using function notation, we would say that f of x equals f of the opposite of x. Opposite x values, same y value. Okay, now let's define odd functions. Odd functions have origin symmetry. So an example of that could be like our cube root function. So if you were to turn it 180 degrees, it would look like it originally looked. If you have the point AB, you will have its image the opposite of A, opposite of B. So opposite x coordinates and opposite y coordinates. So we can put that into words. Opposite x values have opposite y values. And then when we put that into symbols, f of x is equal to the opposite of f of the opposite of x. Opposite x coordinates have opposite y coordinates. Sometimes you'll see it like this. F of the opposite of x equals the opposite of f of x. This means the exact same thing. Okay, sometimes you're not looking at a graph, sometimes you're just looking at an equation and you want to determine if the function is even, odd, or neither. So there's a test for that, or a process. The process is replace x with the opposite of x in the function, simplify it, and see how it compares to the original function. Okay, we'll do that and then we'll talk about how we draw our conclusion. So for problem 2, I'm going to replace x with the opposite of x. Everywhere I see an x. Now, to simplify, you know that if you have a negative and you raise it to the 5th power, it's going to be negative. So basically, the opposite of 5 times the opposite of 5, oops, that's an x, not a 5. Opposite of x, 5 times, is going to be the same as what? Well, every time you have 2 negatives that multiply, you get a positive. 2 more negatives that multiply, you get a positive. You only have a single negative left, so we have the opposite of x to the 5th. So this is the same as just the opposite of x to the 5th. And then the same thing happens with negative x to the 3rd power. It's the same as the opposite of x to the 3rd power. Hopefully you can tell the difference between if I have parentheses around the outside or not, parentheses around the inside. So then let's multiply this negative by this negative, and we have the opposite of x to the 5th plus 2x cubed. Now, let's look at that and compare it to the original function. They are opposites. So we just found that f of the opposite of x is equal to the opposite of f of x. It's the opposite of the original. Therefore, this function is odd. Let's try that on number 3. Here's g of x. Let's replace x with the opposite of x. Now you know when you raise a negative to an even power, it turns out positive. So this is going to be the same as 3x to the 4th minus x squared plus 2, because the opposite of x to the 4th is the same thing as x to the 4th, and the opposite of x squared is the same thing as x squared. So let's compare this, our g of opposite of x, to the original. They're exactly the same. So g of the opposite of x equals g of x. So this is an even function. So you'll want to be able to show the test to prove it as well as draw your conclusion. And I have a shortcut for you, which you've probably already discovered, but the shortcut is not enough to justify your answer. It is enough to have a feeling for what the right answer is. Let's look back at number 2. Look at the exponents. Odd exponent, it was an odd function. Let's look at number 3. Even exponent, and then what about 2? 2 is the same thing as x to the 0 power, so there's another even exponent. 2 is the equivalent to 2x to the 0 because x to the 0 equals 1. So all of the exponents are even. If it's a polynomial function, it's even. If all of the exponents are odd and it's a polynomial function, it's odd. Now, not everything is polynomial. For example, you could have a function that's a square root function, or you could have a function that's an absolute value function. There's other things too, but if it's just a polynomial, you can look at the exponents. Okay, let's take a look at number 4. If you want to apply your shortcut to start with, notice that you have one odd exponent and one even exponent. So what do you think is going to happen here? Let's do the test. Substitute the opposite of x in there. The opposite of x cubed is the same as the opposite of x cubed. And the opposite of x squared is the same as x squared. So when we compare this to the original, it's not equal to it, and it's not the opposite of it, so it's neither. If you wanted to graph the function to verify your answer, you could. Let's just take one of these and graph it on the calculator. So how about if I do number 4? So we had h of x equals x cubed plus x squared Now, I don't know what a good window is for this exactly, but I'm just going to start with a standard window, -10 to 10. So we press zoom. Zoom 6 is zoom standard. Okay. Do you see how that looks a little bit off center? It doesn't look perfectly centered at the origin, so you can see that it's not going to have origin symmetry, and also it doesn't have symmetry about the y-axis, so it's not even and it's not odd. Just for fun, let's do one other one. How about if we do number 3, which was 3x to the 4th minus x squared plus 2. You can see symmetry about the y-axis there. Okay. We're also going to talk about domain. We've talked about domain a little bit, but finding the domain for a particular kind of function can be challenging for students. So I'm going to break it down into different function types and talk about what to look for each time. Polynomials. Okay, polynomials are where, just like you saw in the last few examples, you have x to a power, you just have sums and differences of terms, and the exponents are whole numbers. So f of x equals 3x squared minus 4 is a polynomial. If you want to find the domain, you're asking yourself, what real number inputs will give me real number outputs? So can I square any real number I want? Yes, I can. Can I then multiply it by 3? Yes, I can. And subtract 4? Yes, indeed. So you can take any real number, put it into a polynomial, and you'll get a real number out. So for every polynomial, the domain is all real numbers. You can say all real numbers, or you can use the all real numbers symbol, or you can use an interval, -infinity to infinity. That is true for all polynomials, always all real numbers for the domain. Well then, if that's the case, here's another polynomial function. What's its domain? All real numbers. Because you can cube any real number, it's still real. You can multiply any real number by 2, it's still real. You can add and subtract real numbers all day, they're still real. So that one should be an easy category. Now let's take a look at rational functions. Rational functions look like a ratio where you have some kind of a variable polynomial expression on the top and the bottom. So you might not have a variable in the numerator, but you have polynomials on the top and the bottom. So what you want to think about here is what would make the denominator 0? Because you know you can't divide by 0. So ask yourself, what makes the denominator 0? And you have to exclude that from the domain. Let's make that 0 look like a 0. Okay. So for h of x, number 7, what makes the denominator 0? Well, x equals 2 does. So what's the domain? Everything except 2. So do you want to write it like this? X is not equal to 2. That's okay. Do you want to write it like this? -infinity to 2, union 2 to infinity. That's okay. Either way is good. Here's another one. It's polynomial. It doesn't matter if the numerator is 0. You can always have 0 on the top, no big deal. What matters is if the denominator is 0. So ask yourself, what makes the denominator 0? We can even work it out. What would happen if 3 minus 6x was 0? Then -6x would be -3, and x would be 1/2. Okay, so 1/2 is the number we can't have. So the domain is everything except 1/2. And again, if you want to write it like this, -infinity to 1/2, union 1/2 to infinity, that's okay too. Now let's look at radical functions and think about their domains. So if it's a square root, or a fourth root, or any kind of even root, you can't have a negative inside the root because you won't get a real number output. You'll get an imaginary output, but when we're talking about domain and range, we're talking about real numbers only. So we need the inside of the radical, which is known as the radicand, we need it to be greater than or equal to 0. X plus 3 is greater than or equal to 0. You might be able to figure it out in your head, but you can also write it down and solve the inequality. Subtract 3 from both sides, and you get x is greater than or equal to negative 3. So that's the domain. Here's number 10, same idea, it's also a square root. If it was a cube root, this would not apply because you can have a negative inside a cube root. You can't have a negative inside a square root if you're trying to find a real number. So let's take the radicand. Oops. And say it has to be greater than or equal to 0. Subtract 5 from both sides. And then when you divide by negative, don't forget you have to reverse the inequality. So x is less than or equal to 5. If you're doing it in your head instead of writing it out, your question is, first of all, what makes it 0? And then after that, figure out if you need to go above or below that number. Okay, now our last couple are going to be combinations of those kinds of functions. So here in number 11, we see a radical, but it's also in a denominator. So if it was a radical alone, you would say that x plus 6 has to be greater than or equal to 0. However, because it's in the denominator, we can't let the denominator be 0, so we're going to have to just say x plus 6 is greater than 0. Subtract 6 from both sides, x is greater than negative 6. That's the domain. And by the way, you don't have to write it that way. You can write interval notation if you want to. And then last one, same idea. We have a radical in the denominator, so the radicand 3 plus 2x has to be greater than 0. We'll solve that for x. It doesn't matter about the x on the top because you can have 0 or any other number on the top. X is greater than negative 3/2, so that's our domain. And if you want to write that with interval notation, that's fine. Okay, I hope you don't mind if you have a bit of a short assignment today. There's not a whole lot of practice in your book on this topic, and hopefully that will be sufficient. So when you're doing numbers 31 through 36, be sure to do the test where you plug in the opposite of x and you simplify and you see if it comes out the same or the opposite or neither. And then if you need help on 34 and 36, there are some tutorial videos available. Thanks, everybody.